probably the most conceptually most difficult is going to be now. So it's I'd like to show you something that is kind of tricky, and pay attention. First of all, I choose a data set that has a bit more, a higher number of features actually. So I went, there's a widget called datasets, and there are a number of data sets here, but I'm going to pick the one, again, apologies, not related maybe to your work, but perhaps interesting. And that is, it's called employee attrition. Basically, this was created by IBM. It was created because actually there's no company that is going to give this data away. So basically the data is about happiness at work, right? Or it could be also happiness at studies or happiness anywhere, right? But it's about happiness at work. So let me show you the data. But basically, yes means that if somebody says yes when is not happy about the job and says bye, right? And the whole data set is actually, the idea of this data set is, can you detect unhappiness at work before somebody leaves, right? So the same problem occurs in any kind of sales, banking, right? People leave companies and banks, and so these kind of things we do in life quite often, right? We are attached to something and then we say, okay, we have enough, and we leave, right? Right. And so there are a number of features here, like age and how often do they travel, and which department they work for, and what's the distance to the work, and what's their education, and gender, and how much are they paid, and the job level, and current satisfaction of the job, and whether they're married, and monthly income, and whether they're over 18. That's strange. Okay. Whether they work overtime, right? Do they have some shares of the company, the total working years, and so on. So all these factors, right? And the question is, not only, can I build classification tree? Because of course, yes, I can build classification trees on this, but how accurate is my classification tree? Okay, or how accurate is, so when I predict, right, I would like to know how accurate I am, because if I'm not accurate, right, then my model doesn't make sense, right? So whoever I'm going to invite for a special discussion, right, human resource department will not know whether, I don't know, is this guy really leaving the company or this is just random, right? So what's the accuracy of the model, right? A warning here, I'm going to trick you in the next 15 minutes. So I'm going to go somewhere where I shouldn't go, and then I'm going to tell you what is the right path. I'm going to trick you so that I'll be a bit faster, okay? So what I'm going to do, okay, I'm going to build a tree. Here the data is quite complex, and the tree is not, so the tree is not an easy one, actually. It's, so this is just the top of the tree. Turns out that one of the main factors of unhappiness, right, is that if they work overtime. So people that work overtime are not happy, right? Basically this says, right? The attrition actually is raised for the people that work overtime and the people that earn less, right? So that's what tree is telling us in the topmost branches. But I'm not going to go into interpretation. I'm going to venture into interpretation in the second hour. Here, there's another concept that I would like to work. So now I would like to see, okay, how precise is this tree, right? So basically what I'm having here, just let me look at the box plot. And then I have attrition here. Okay, so there is a fraction of people that leave, right? 247, and there's a fraction of people, a larger fraction of people that stay. So those that stay at a job that don't leave, right, are luckily in majority, right? 83% of the people stay, actually. So I'm going to build a tree on that. I already did, right? I would like to know how accurate is this tree on the data. There's a widget called predictions, which receives a model. So a model is the tree that I just built, right? And also receives the data. So the data is here. And then tells me actually, so this one tells me, okay, this is what the tree predicted, right? And we see that here for the first employee, the tree predicted yes. So that one's going to leave. And the true class, sorry, this is the true class here is also yes. So the prediction was correct, right? And then I can scroll down and I can see that sometimes, I mean, there should be some errors here eventually. Maybe I can sort it by, can I sort it by no? Yeah. So you can also see that the trees predict probabilities as well, because sometimes the final leaf is not clean, and then some of the instances go into one class and some of the instances go to the other class. So this is where you have this prediction, which is like sort of probabilistic, right? It's not 100% no or 100% yes. And then there should be some errors, but I'm not detecting a lot of them, almost no error here. Wow, so that should be kind of excellent in terms of prediction, right? So whenever the tree says no, the true class is no. Here are some errors, right? So here the tree said no, whereas the true class is yes, right? So basically the idea is that maybe I should count. So maybe I should do something called confusion metrics. Confusion metrics is saying, okay, what did the tree do and what is the true class? So here I see that out of so this is the actual class, no and yes, right? So there are 237 people that actually left the job, right? Of which the tree predicted yes 193 times, which is okay, right? Because I mean that looks good, right? And out of 1,233. Almost everybody, right, that the tree predicted no, they were truly in the no class, right? It's also okay. So currently I'm showing this for the attrition for the data set, and this sort of looks okay, right? It looks here, it doesn't look perfect, right? Because the number of yeses, so a number, when the class is yes, right, the tree quite often predicts no, right? But it's still, in general, it's okay, right? So if I sum up, so out of 1,470, if I sum up the correct guesses, there's a measure called classification accuracy that says, okay, classification accuracy for this data set is 1,224 plus 193 divided by 1,047, right? And that is actually reported also in the predictions, and it's this one, this column, classification accuracy is near 0.96, okay? So 96%, right? So this classifier is 96% correct. Is this a good classification accuracy? Okay, there's much more behind that, right? But for now, fine, right? If we would know, for instance, that, I don't know, the quick tests for corona are, I mean, for COVID-19 are 0.96, they're 96% correct, right? I mean, the general public would also say, oh, fine. All right, now that I convinced you into that, right, let's do something here. So here, now I'm going to destroy the data. So now I'm going to take this data set, and you have to trust me on this one. So I'm going to randomize the classes. Okay, so basically what I'm going to do, okay, so here is the classes are the classes are this column on the left, right? Column on the left tells me whether somebody left the job, right, or somebody stayed. Yes, it's like somebody left, right, and no is that somebody stayed. So the reason why, I mean, at least we think so, right? The reason why this tree predicts well, right, is that there is actually some relation between the profile of the person, right? and the attrition, right? Okay, we saw that the relation is, okay, if somebody works overtime, right, then it's more likely to leave, right? And if the monthly income is low, right, it's more likely to leave, right? And then, I don't know, this is obviously American data. So the stock option, right? If somebody has an option to buy some shares, right? Probably those that have this option, they stay, right? And they don't leave, right? Because they hope they're gonna cash in, right? So there is this structure, right, in the data. One way to destroy this structure, like the simplest way, is that I would take this column, attrition, and I would randomly shuffle the classes, okay? Randomly shuffle means I would just basically the assignment, whether somebody leaves or not, is going to be random. So after the randomize, so I have exactly the same data. So I don't know, the first one also 41H, right? Age 41, travel rarely, daily rate the same. So I'm leaving everything on the right? But I'm changing the column. So where, I mean, okay, first one is still yes, right? But then see the first one was yes, here is no, right? And the 11th one was before no and yes. So now all these labels are random. The labels have been shuffled, right? And I just reassign the labels, right? And by doing that, right, I really destroy all, I mean, if there was some relation in that data between the class and the other features, right, it was destroyed by doing that. Okay. Also, before I go ahead, maybe just as evaluation results, maybe I'll just do something. I show you the distributions of what the tree predict and what is attrition. Okay, so this is just graphically what I was showing you in confusion matrix, saying that, so graphically meaning that attrition tree, yeah, this is just a graphical depiction here. So here I'm showing if the tree predicts no, then majority of the cases are really in the no, right? And there are just a few errors here. So this is just graphical depiction of the accuracy, right? And with the tree predicts yes, right? The majority of people really left the company, right? And here in this bar here, right? In the blue one, I have those for which I made a mistake. So all mistakes are here, right? So basically there are 44 mistakes here, and then here are just a few of them. There are 9 mistakes here, exactly like what confusion matrix says. So 9 and 44, but I just have this graphical presentation, right? Just to say that here majority should be blue and here majority should be red, and I'm fine, right? Because the tree predicts well. Okay, just to know, right? So I'm going to do now the same, right? But on destroyed data, right? So on completely randomized data. Completely randomized means that I shuffle the classes, okay? So I'm going to repeat this procedure for this randomized data. And what do I expect here? What kind of distribution should I get? What do we expect? If I build a tree on the randomized data, what's going to be the prediction accuracy? So I'm again predicting from the randomized data. I'm testing on the randomized data. I'm actually getting and then of course I can do the confusion matrix, but I'm going to do the distributions here. Okay, so in orange I can do that fast, right? So, and then I get this. So the tree and the attrition, right? And this is what I get, right? And my question is that something that I expected or not? So does this look good? I mean, is that similar to this one? So this one is on the true data, right? Is this conceptually much different or is similar? This actually looks great, right? I mean, this one looks great. I mean, we didn't expect that, right? Because we messed up data is like really messed up data. We didn't, I mean, this works like magic, right? So the tree, right, can even predict when the data is completely random. I mean, how is this possible, right? So I'm taking the data, right? I'm building a model. the data is completely messed up, right? And then, although it's messed up, I'm still getting great results, right? It's like, works like magic, right? People would say, oh, machine learning, that's great, right? Even from completely random data, I can do the stuff, right? These are not predictions, what I'm doing. These are not predictions at all, right? These are just trying to remember everything that it's in the data. Actually, the trees here, right, that I'm constructing. So I can actually view the tree here. The trees here try to memorize all the training data here. So the tree is absolutely huge. It has 330 nodes and 157 leaves, and there's no way I can display the tree. I mean, there is a way, but the tree is huge, right? And it memorizes everything, right? Memorizes everything to the point, right? Let's see if this is possible with ARIS. So ARIS is much simpler, right? So ARIS has this nice scatter plot like this, right? If I randomize the classes and I show you the scatter plot, the same scatter plot is going to look like this, okay? So now it's the scatter plot has the same shape, right? But the classes have been messed up, right? You see that the colors, right, that refer to the class are, so now I have this mixture, right? And one would say that from this, right, there's no way I can predict anything, right? So if I do the tree here, maybe that's even better example. So if I do the tree on the original data set, the tree looks kind of simple. We've been there yesterday. Tree viewer. The tree is very simple. This is the tree that we said that we can write down and then go to the flower shop, right? And it's going to be okay, right? But after I randomize the stuff, right? So the tree, it's no longer simple, but the tree looks like this. So it's much more complicated, okay? But I still get very pure leaves at the bottom, right? Because what this tree actually does, right? It takes this scatter plot, right? And try to build boxes around certain areas, right? Maybe these two blue ones have a box around saying, okay, here, you know, for these particular values of petal length and petal width, I will actually predict this stuff, right? So basically the tree, what I wanted to say, the tree that I'm building on a randomized data remembers all the points. So the model got so complicated, it remembered all the points, right? So here you see that, well, sometimes there are some errors here. So here, there's going to be an error, right? So one of the four will be an error, but here it's okay, right? So the leaves are sort of, they always go to almost the one class, right? Sometimes they miss, right? But not often. And because if I then say, okay, I would like to do the predictions on the same data, right? Of course, the predictions will be almost correct, almost always correct. So classification accuracy here is 80%, which is still high, right? But it's because the tree remembers. So the model got so complicated. Okay, this is because I'm actually testing my model on the training data. So first I give the data to the model, right? And then I say, oh, what's the accuracy on your data that you already seen, right? And if the model is versatile enough, right, it's going to remember everything. And that is called overfitting. Overfitting is when you train the data, when you try to remember everything on the training data, right? And then if you report the results on this data, your results will be overly optimistic because you remembered most of the data, and this is not the prediction, right? Although this is a trivial concept, I mean, in a sense, right? It's interesting how many times people get it wrong. I just reviewed 5 papers for one conference. One actually reported the results on the via the overfitting. So they they use the data, they use the training data and then reported the results on the training data. It's amazing, right? And used to be that, I don't know, 20 years back, half of the papers actually did this mistake in some way, right? So this is, it looks trivial, but it's not, right? Okay, maybe just what is the solution? How can I test my model, but in a correct way? I mean, in general, right, what should I do here in order to get the right course? I mean, in order to assess the classification accuracy, what should I do? My training data should be separate from the test data. Okay, I should really, I mean, the way that I can do, right, I can split the data into training and test. Okay, so what I'm going to do here, I'm going to take 70%. I can actually adjust that, but just to keep it simple, right? I'm going to take 70% of my data, and I'm going to train the tree on that data, okay, on the 70%. And then I'm going to test the accuracy on the remaining 30%. So basically, I'm going to split my data. So this is the data, right? And then I'm going to use 70% of the data. I'm going to build a tree. So I'm going to build my model on the 70% of the data. So training, right? Training. And then I'm going to take this remaining 30% of the data, and then I'm going to test it. So test. And then I'm going to report on classification accuracy, or any kind of accuracy will be measured on the test data. So I'm never going to use my training data for any kind of testing, okay? And the widget that breaks this, that can break to 70-30%, right? The widget is called the data sampler. So I'm sending the 70% of the data to the tree, which is called 70% is like the data sample, right? The sample. And then I'm also going to use the predictions widget, but I'm going to feed the data that I'm going to feed the predictions, that I'm going to make the predictions. Well, it's not data sample, but I have to double click here. It's going to be the remaining data. I have to rewire this, okay? So now 70% of the data goes to the tree, to the inference of the tree. I build a model, and then the model is tested on the remaining data. So in the data table, if I have a data sample has 1,029 instances, but the remaining data has 441, right? So the remaining data is smaller, just 30% of the data, right? And this is the data where I'm testing the predictions. And let's look at the predictions now. Well, the classification accuracy dropped quite substantially, right? So before, when I tested on a complete data, right, was 90%, right? Or what was 95, right? So basically, I should never, right, report the accuracy on the training data, because that one is going to be higher, right? I shouldn't say the true accuracy, right? But my estimated accuracy is actually 78%, right? Although maybe that depends on the sample, right? So here I can say I will unclick replicable sampling, because with this I always get the same sample. And then here, when I sample, right, it's going to be a different sample. So each time I'm going to use a different sample. And you can see that my classification accuracy changes, okay? So every time I sample the data, oh, now it's 79, right? And then now it's 78, even worse, right? I'm looking at this guy. Oh, now it's 84, right? 84 is actually good, right? I mean, this is also one way of cheating, right? If that process, right, depends on my sampling, my accuracy based on a particular sampling, because then I can cheat, right? I can press sample many times, right? And then I'll just report the one that is the best one, right? So I'm cheating, right? Basically, what people do, right? They say, okay, I mean, I really have the distribution of the scores under different sampling, right? So what I can do is maybe I can press sample data 100 times, and then report on the average accuracy that I get. Okay, the problem with that would be that this would not be an accuracy of a particular tree. So I will not say that this is an accuracy of this particular tree, but an accuracy of the process of building a tree and then testing it on the test data. So an accuracy of the modeling technique, right? Because I'm actually making 100 trees, right? And then I'm averaging the accuracy. And so I would say that, okay, if I build a tree from the entire data set, I would estimate the accuracy on the unseen data, right? So that's kind of important. So this is now, I'm turning orange into I'm building actually a process of how to estimate the accuracy of this particular method. And of course, it's tedious to do this 100 times, right? So there should be a widget that does this 100 times and actually reports on the average accuracy. And the widget is called Test and Score. So it's so Test and Score is the widget. This is sort of conceptually, it's an interesting widget. It's so it's gonna so it has actually a number of ways how to do the test and scoring, right? One of them is random sampling. Random sampling is that you can repeat the process, let's say 100 times. So the test and score would actually get the whole data, but then it would sample the data and then give one sample. So let's say, I don't know, 70% of the data to the modeling technique. It would build a model and then test it on the remaining 30%. So it will do exactly what I was doing now, right? And it would also average the accuracy across, I don't know, let's say 10 times of repeating train and test, right? So it doesn't do anything now because there's no modeling technique. Right? So I'm not sending the model, right? So the tree, if this widget gets the data, it would output the model. So this one, but this one instead, right, outputs a learner. So learner is just one of the outputs of the tree. So this widget outputs an algorithm of how to build the trees, how to build predictive model. And this algorithm is then used in the test and score on the 70% of the data. And then this algorithm spits out the model, which is then used on the remaining 30%, okay? So there's actually no tree here, right? The tree is built within the test and score, and then it's tested within this, right? And then this repeats, so the test and score repeats this training and testing phase 10 times, and then reports on the classification accuracy, and the classification accuracy is 80%. All right, so it's substantially lower, right? So 80% is not high anymore, right? And it's actually kind of low, right? Is 80% in this data set, is that sufficiently okay or not? I told you that basically I should never estimate accuracy on the training data. I need to do that on the test data, right? I also told you that I should do that several times, right? In order to, because then to actually remove the dependence on the sample, right? And now I'm asking you, so so now I'm in this third phase, right? Where I'm asking you, is 80% all right or not?
Well, probably not really, because it's 1 to 5 wrong.
Yeah, so 1 to 5 is wrong, right? But in general, is 80% okay or not? Right, I go to Las Vegas, right? And I'm having this box, which is a predictor, right? So they are throwing a dice, right? And there I have some cameras and so on, right? And I'm predicting where the dice is gonna fall, right? And I'm predicting with 80% of accuracy, right? Is that high or low? So the answer, right, for the accuracy, right? It depends, right? It depends based on how difficult the problem is, right? So how difficult is this problem I'm having, right? So if I go to the box plot here, and then I look at the distribution of attrition, right? I see actually that there is the no, right, which is 83%, right? So 83% of people stay. So if I would have a model, right, if I would have the craziest model, right, that would say, so when the employee comes and I say, oh, everything's fine, you're okay, right? What's the accuracy of that particular model? It's 83%, right? Because I get all the no's correctly. Okay. So I would correctly predict all the no's, right? Okay. The other thing, right, is that I would not, I mean, my sensitivity to the yeses, right, is 0. Okay. So I would fail on yeses, right? But who cares? Because my classification accuracy would be 83%, right? So basically, when if people just report the classification accuracy, right, without knowing what is the distribution of the class, right, you can throw that away, right? It doesn't mean anything. Okay. The problem here is in distribution, right? And the problem here is that classification accuracy is doing even worse than a predictor that would say no all the time. Okay, so 80% is not okay. The fourth thing is that let me do the sample now. So I'm going to data sample, and I'm going to do the trees here again, and I'm going to look at the tree, but then I'm going to use some other visualization for the tree because the trees are for this domain too big. This is actually called, this particular visualization is called the Pythagorean tree, right? So the root is here. So these are all the cases are here. And then they're split to one branch and the other, right? And the leaves are at the very end. And I expect that the leaves will be colored. So you see where the red ones are, those are yeses, right? So those are the people that actually they will leave, right? So sometimes you would have the red leaves. Dark red leaves means that the group of the people that leave were detected, right? So there is one branch here that is more reddish, and there is one branch here that is more reddish. So this is the tree. But look what's happening if I change. So if I change my sample, the trees are completely different, okay? Trees are inherently unstable. That's the major problem with the trees. Okay, because if you change the data a bit, right, then probably the feature that splits the data here on the top, right, would be some other one, right, and that would change the entire structure of the tree. So the trees are really unstable, completely unstable, right? So, which is a problem, right? Because it's a problem in interpretation, right? Because if you build a tree and then you say, oh, you can interpret the tree, right? That it's not so strong because under slightly different data, the tree can change completely. So your interpretation would refer to something that is not stable, right? And this was noticed about 20 years back, this instability of the trees, right? And there was this guy, Leo Breiman, who actually invented the trees in the first place. And he was saying, we should put that into advantage. There's on the TV, the series is How to Be a Millionaire. You have, 15 questions, right? And with every question answered correctly, the amount of the money you would get doubles, right? And then you can stop at a certain stage and say, okay, I'm gonna take all the cash that I earned and buy. The questions are getting harder and harder, right? And then when it gets really hard, you have these free sort of jokers, right? And one of the jokers is you can ask the public. There are 4 possible answers. And people vote, right? And then they display on a TV the results of the voting, right? And usually it's so that one of the answers prevails, right? And then usually the one who's answering right would pick that majority answer, right? And why does that work? I would assume, right, that the question is so hard, right, that probably majority, like maybe 50, 60, 70%, right, of the people in the audience have no clue about the answer. So those that don't know anything, right, they would vote randomly, right? But those that know, right, they would bias the answers towards the right one, right? So voting by majority is great, right? We can take samples, right? And then majority of the trees will be sort of random, right? But out of some of the trees will actually know something, right? And so instead of building a single tree, right, I can build hundreds of trees, right? And these trees would then vote on the class. So this procedure is called a random forest. So instead of building one tree, I'm building several trees, and so I can build a random forest. And here actually I'm building 10 trees. 10 is default in orange. I'm going to increase that to 100 trees. And see now the accuracy, right, actually goes up, right? So it goes up from 0.8 to 0.85, right, which is above 0.83, right? So this suddenly makes some more sense, right? And then I'm seeing also there are some other things. AOC tells me if I take a guy that does not live, and I take a guy that lives, is the probability that I will correctly discriminate between those two. So I know that one lives and one doesn't live, and there's a 50% chance that I'm going to correctly guess by random who's going to live or not, right? But if I'm informed, right, I'm going to recognize the one that's going to live better, right? And this one says that the random forest, when given a pair of live and does not live, right, in 80% of the cases, it will find out who's the one that's going to live, right? And here the tree is going to be almost random, right? Only 50% or 56% will be recognized. Random guess will be 50%, right? So, but just by saying, okay, so the random forests are better than the tree, right? In reality, right, the random forest now is almost like the method that the people used in classification. So if, and the trees are not. So the trees are interesting, right? But only to introduce random forests, okay? So if you want to have accuracy, right, the random forests are way better. The problem with the random forest is that if I apply a random forest to the data, and then I check out how the random forest looks like. So these are all the trees in my. I'm not having a clue how this works. Okay, I cannot interpret this model. This model is especially not only so here are the 10 trees, right? If I'm building 100 trees, then I lost interpretation. Okay, and then there are some other methods where. Which work fine as well, right? Are very simple as well, right? And then they have interpretation. One of them is logistic regression. It's probably the method I always try. And just let's see how this works. So random forests are nice, right? And random forest is something that I always try. And if it gives if it gives high classification accuracy, then okay, right? But sometimes this is a way simpler model, the logistic regression. Sometimes this works as well, right? And here it's even better, right? So I'm guessing, so classification accuracy is here 0.88%, right? And this AOC is 83%, which is like 85% is like the magic limit where for a model, I would say it's going to be useful in practice. So this comes pretty close, right? And often it is strange that logistic regression beats random forest, but my assumption is because this was a fictional data set that was created by IBM, I would actually say that IBM used something similar to logistic regression when they created the classes, classification accuracy. The problem, of course, with random forest is that it's impossible to interpret them. So I lose interpretation, but I gain in accuracy.